SwayamPrabha. Digital India. Educated India.
Good morning everybody. We are continuing with our discussion on how hydrodynamics is affecting combustion stability, and then we also looked at how vortex itself makes sound and causes some kind of aerodynamic noise, and we looked at it in the context of solid rocket motors, and I was also talking about the lock-on between the vortex shedding frequency and the acoustic frequency, and this is also similar to the case with flow structure interaction and vortex acoustic interaction and vortex acoustic combustion interaction. And in this context I wish to give you a reference of a very famous paper by Professor Ho titled Contributions to the Theory of Aerodynamic Sound with Application to Excess Jet Noise and the Theory of Fluid in Journal of Fluid Mechanics, volume 71, issue 4, 625 to 673. It is a very big paper, almost 50 pages, and it is a very famous paper. You see that rockets and fluids, they are all behaving in a similar way. So a little later we will speak about the fluid. I have brought some fluids with me and we will speak about it. But talking about the lock-on, and we will see if these concepts are applicable in dumb combustors as well. So when we look at flow structure lock-on, we look at the dominant frequency that you see, frequency versus Reynolds number, and right below I will plot amplitude versus Reynolds number, and the vortex shedding frequency we saw it scales by a characteristic Strouhal number. So if you have a Strouhal number which is FL over U, then F will be equal to ST into U over L, or rather F is proportional to U, and therefore frequency will increase with Reynolds number in general, because as you increase the velocity you will increase the Reynolds number. You can plot velocity also here. So as you increase the Reynolds number, usually the frequency keeps going up of vortex shedding. But then what happens, so let us look at the case of a structure. So if this is tied to a structure, like for example in a case of a cylinder sheds vortex, but if the cylinder is mounted on a spring or something, and then the spring mass system also oscillates. Or another example would be, I mean the same kind of situation occurs in underwater cables where you have flow and then it sheds vortices, but the cable itself can move around or vibrate. So you come near, so let us say this is the frequency of the structure. So this is Fv goes like this, Fs comes like this. So when so as you increase the Reynolds number, your frequency comes like this, and then suddenly it locks to this structural frequency, and both the structure and the vortex, structure will vibrate at the frequency and the vortex will start also being shed at the same frequency. Everything will work together and then it will go up, and of course there will be some hysteresis when you go this way and that way, but otherwise this is the pattern. And the amplitude would be, when it will be like this, it will gently increase. Naturally as the velocity is increasing you will get more noise coming out, but as you approach this lock-on there is a sudden rise in amplitude, and then there will be a decrease in the amplitude of the vibration or the vortex strength or whatever. So if you are looking at a pipe, usually you can excite several modes. So if you are looking at that solid rocket motor or a flute or something, you can have maybe more than one harmonic, whereas in structure it depends, it may be possible to go to another harmonic and so on. So if you have such a situation, and let us draw this graph again. So this is structural acoustic lock-on, I would say, sorry, vortex structure lock on, okay, or it is like flow structure lock on, vortex is like flow. Now if you look at we look at vortex acoustic lock on, so we will have dominant frequency and Reynolds number, same graph, same scale, Reynolds number versus amplitude, and like I said, the same scaling of Strawell number happens, so f will keep increasing, but then as it increases, let us plot also these are the various duct modes. If you have you can have a closed open duct or open duct with approximate formulas as what are the formulas for closed open duct and open duct for the natural frequency? C by 4L, 3C by 4L, 5C by 4L, and if you have open pipe, C by 2L, C by 4L or whatever. So we just symbolically, I do not worry which one it is, but we will symbolically mark, and they are constant, and we mark those frequencies, and when and you increase the Reynolds number and the frequency keeps increasing, and then it will switch to one acoustic mode, and then it will switch to next one and next one, and maybe after that it cannot lock on, so then it will just climb like this. So this is and then the amplitude would be I mean the exact features it depends on the experiment, but and depends on the actual amplitude depends on how the damping is in the system and how that depends on the frequency, so many other factors, but this is like a schematic of how the amplitude will vary. So when you have this lock-in situation, some people call it lock-in, some call it lock-on, when that happens you have the vortex shifting frequency and the tube's frequency, duct modes or tube mode, they will be exactly the same frequency. You can measure them. For example, what we did some years back, maybe it was in 1997 or 98, so we measured the vortex shifting frequency behind a orifice, which we were trying to simulate the inhibitor in a rocket motor. So we put a hot wire anemometer and then we were measuring, and this value was exactly same as the acoustic pressure frequency which you measure in the acoustic field, whereas if you did not have this lock on, you will have broadband spectra and there is no precise matching of frequencies, and the vortex shifting frequency may be different from, it will be quite different from the acoustic natural modes, but when they lock on and they are exactly precisely same, and you can see to several decimal places, and this is like a non-linear interaction. Any questions about this? Yeah, beyond some period, in some range this locks in, and beyond that it does not occur. Now precisely how many modes it will lock on, how many it will not lock on, etc., it is hard to tell. There are some cases when in our experiments we have managed to lock onto the 8th mode and 9th mode and 10th mode, but the lower side is because you can't lock in below this because there may be no acoustic mode, and above that the damping may be too much, that you get certain driving from the vortex which will try to drive the acoustic mode, but then that may not be sufficient to get the amplitudes to go up because the acoustic damping of those modes may be very high, but precisely how many modes can it lock and all that depends on the actual case, but in generalities this is what happens. Okay, so we will I have brought some flutes with me and some bottles, so we will look at this, and just to get you an idea, first we will look at the flutes. These are Carnatic flutes mostly, so got whole bunch of flutes. So you can see it has holes here and it is a straight passage, and of course they there is nothing burning here, but the characteristics is very similar to combustion in the sense it is duct acoustics. And so you excite lock onto the cavity modes here, and it is in general close to the what kind of mode? Open mode actually, whereas they say that some other wind instruments like clarinet, I have never played a clarinet, so I do not know how it even looks like, seen it only from a distance, but this one is more like a open, and although you could tend to think that this side is closed, but there is a hole here, and this here when you play you keep certain fingers certain way, and so the last hole you close, and then that determines the effective length. So this kind of makes the pressure equal to the atmospheric pressure, so then the effective length becomes from here to here, and open duct mode. There will be some slight difference, but that is kind of what it is. So what you do while blowing is, so what you are doing is I am grazing this, and of course there are different flutes work differently. There are some other flutes which have a labium, like you have a reed kind of thing. I have, so you blow this way, and then this is a PhD thesis on flute, and you have what I mean, and there is a sharp edge here, there is another sharp edge, and this vortex comes hits on this, that kind of it. So this is another kind of flute with the reed. I think these are the ones, if you go to the Marina Beach and you can buy flutes. I had one of them, but my daughter has taken it and she is not giving me. So you blow this way, and then there is the flow goes this way, and then it interacts with this edge. Okay, that's the way it is. Sorry. Yeah, but the yes, some jet comes out here, but I think the interaction is with this edge. So if this is not there, the sharp edge is not there, then it won't make sound. And this is, people have done Leiden photographs and flow visualization and so on for those things, and you can see this is like how the vortex is coming and rolling up and so on and so forth. I don't want to project slides with this because that is copyright violation, so I will just show you this book. And so first thing you can notice is, let's look at the flutes and make out some of this. This is a short one and this is a big one, and I mean you can see if you go to a Carnatic music concert they use different flutes, whereas in Western music flute they use the same flute for different ones. So sometimes they use the short flute, sometimes we use big ones. When do you use big one? When do you? Yeah, so lower pitches you can use the big one, and because it will have a inversely proportional to the length, that is what it is, and so this is a smaller length, so it will be higher frequency, and you can will play sa in this and play sa in this, and you can see whether it is actually different. So that is try to remember that note. So this is significantly higher frequency. I think this is on says C sharp and this is G, so I mean significant difference in frequencies there, and you can also notice that so the you move your fingers and that's how you get it, but then had this lock-on phenomena been not there, you would have to precisely, to get certain frequency you will have to precisely blow at some Reynolds number. That would be incredibly hard because you also use the blowing power to increase the volume or decrease the volume. Also, so what you do is, so you do not have to be so sharp, and that way you can use the a little bit of this Reynolds number range, I mean to control the volume. So it is not like the flute player is critically calculating, okay, this frequency, what is the critical Reynolds number? No, he gets within some range, so, and then when he goes to a harmonic he blows the same note, he blows harder. I will attempt to demo this, but if it does not work we will have to edit it out. So that is I mean I went past this critical Reynolds number and then I reached this frequency which is the harmonic, but I am not like looking at a flow meter or a Reynolds number meter to figure out, it is just if you play you will get the feel. And now is there anyone who know how to play a flute here? No, just try playing it, let's see what happens. Yeah. We'll see if flow acoustic, I mean vortex acoustic lock on happens or not. So just make so this is like a broadband spectra. So the vortices by themselves they have some coherence, but play again. Okay, so he's getting more coherent, but the first time it was more like a oof. So and Viksha, you can try just get an idea. You have seen flutes in concerts, but let's get some practice how you yes, don't destroy them. One more. This is actually a North Indian type one because it has 6 holes. The South Indian ones have 8 holes. Everybody can practice and we can record how they just blow. I mean, please. Yeah, that's. Now you are like. That's good. So you somebody who does not know, can you play? Right, that is very good sound in which we are in this range, we are outside the lock on range. Okay, that's enough. Okay, so so if you, okay, so Ganesh is locking on, but if you are having this that kind of sound, then I mean we are you can clearly see that we are having like a broadband sound as opposed to very tonal sound, and we are not locking in, and we really need to get a sharp frequency, and our natural frequency duct, they are very sharp, very narrow bandwidths and very sharp resonant peaks, and that's what it is. And the one more good thing about the flute is it can sustain several harmonics, so which is why flute sounds very pleasant. So now in flute, lock-in is very good, you can get pleasant sound as opposed to this which you have been at least many of you have been successfully generating. But in in a rocket or something, if you have this coherence and nice tone, that means the amplitude will be very loud. In fact, when you made this lousy sound, amplitude was also low, but with the nice sound the amplitude is also low because you are putting everything into one frequency. So you can imagine in a rocket, I mean you have a very nice lock-in, and then your amplitude will be quite loud, and then of course this here the pressure oscillations are I mean smaller than Pascal or of the order, there it is like several bars or 1 bar or something like that, and then you can imagine things coming loose and breaking up and so on. So but the same idea can be used to get I mean to analyze and so on. So first thing I did when I started working on the rocket motor instability with the inhibitor is to read this paper and some other papers and then get an idea. So I think if you learn about wind instruments, I think you can get a very good idea about this lock-in phenomena. So what do we say, I hope you saw this clear lock-in phenomena. It also depends on the grazing angle, which is what you guys are struggling to get many times, and if you blow too less or too hard, you would be outside the range. So here we are locking onto the tube modes or the duct modes. Now let's look at the example where we are locked. See, if there is a vortex and if there is something to lock onto, some other frequency, it will lock onto. Of course in this case, when you tried, for example, the foo sound came because you are trying to lock on, then you don't get lock on, but if you don't want to lock on, it will lock on. That's the way it is. So let me give another example. I have brought some bottles here, and here we will not have tube modes but some other modes. So we can actually, Bala was speaking about the Helmholtz resonator. So this is like a Helmholtz resonator. I think he derived the formula. I will ask you in the exam how to derive the formula, but at the moment you can believe that see, okay, let's compare. These are approximately similar frequencies, right? I mean similar lengths. So I will without any formula for Helmholtz resonator and all that, I will demonstrate. I don't know if I have a smaller one. There was a really small one somewhere. No, another. Yeah, that one. I don't know if that's its length is. Oh, it's almost same. So okay, so this a little bit difference is there, but it shouldn't be. But you will see order of magnitude difference in frequency. So let's listen to the flute. okay, and let's listen to this. Okay, so I kind of cheated, I should get this frequency, so that is, then it will be, yeah, if I get pa or something like that, then okay. Now let's look at this frequency. So this length is I mean I was closing till here, so it's approximately the same length. Hope it works. It's way low, way too low, right? So it's definitely not a tube mode, it's not C by 4L or C by 2L, but it's the Helmholtz mode. So here also the bigger size means smaller one, so let me try this one. This is definitely smaller volume and so on. Definitely this is having higher frequency than this. So you can take all bottles and construct a musical instrument actually. This is even smaller. Okay. So there I had to increase my Reynolds number to lock in, right, because I was blowing at the here I was blowing very softly and I was peacefully able to lock on, and here I really had to blow much harder, okay. So because this thing's frequency is higher, so and the lid sizes are approximately same, so I really have to increase my velocity to get to a range where I could lock in. So it's let's see if this works. I may have to drink some more water to. Now if I drink more water, the frequency will come down. Yeah. So anything is there to lock into, it will lock into. So if there is a cavity, it will lock into the frequency of the cavity. If that is what we are having here, and all I am doing is just blowing like this. So there is a vortex being shed, and the acoustic velocity is, the vibrations are this way, so I am blowing it perpendicular to it, and that is when the maximum power comes out. So there are people who have taken movies of such things, and this is a very similar situation to side branches. This is a picture of the side branches, and you can see these are Schlieren pictures. And if you wonder how you can take Schlieren pictures in a cold flow, normally you think of Schlieren for supersonic flow and so on. So they inject a little bit of CO2 somewhere there and then do Schlieren, so the density change is like, it's like putting smoke but more convenient. And what else? So is there any question on this? If you have a vortex shading, and if you have a spring mass system or some kind of springiness in the system, as in structurally, you can lock to that. Like if you have a cylinder and then cylinder is mounted on spring and mass, that is a system which is studied very well, and the rigid cylinder patterns, vortex shading patterns and frequencies are different from when the cylinder is mounted on a spring and so on. And so this is interaction between two resonating systems. So flow structure interaction is one of them, flow acoustic interaction, and now we look at flow acoustic combustion interaction. Before that I will pause and see if you have any questions on this. I thought it was simpler to show these things this way rather than write formulas and so on. I hope you got an intuitive understanding. So now the next question is, what happens when there is a vortex acoustic coupling in a combustor? So there is a combustion vortex acoustic coupling. Would you get this pattern, or would you get some other pattern? So it's a little tricky question. In fact, people believed that it was the same thing that was happening, but it turns out that it need not be. There is another scenario which I will present here. This is a recent discovery. So this is Reynolds number and amplitude and Reynolds number. So vortex shading also has several modes. So let us draw two modes here, okay. So you can if I with the same orifice you can have several modes of vortex shading, the first mode, second mode. So and if you have a cavity this way I can have one vortex always, or I can always have two vortex between them, and so on. So there are many modes there, and so you have this duct frequencies here. Look for the color chalk. So the so you can actually have, of course, both the duct modes and the when the lock on is not there, you will see, you can see if you make microphone measurement both the vortex shading mode and the duct mode, but then when the lock in, actually the duct, I mean the acoustics locks to the vortex shading, it seems like, because I mean the actual details are not clear, but this is a new finding. The vortex is causing the periodic thing, and the acoustics is probably changing the boundary condition and all that to lock onto this. So this is reported by our IIT Madras people. So instead of the vortex shading frequency locking the acoustic, here the sound locked to a vortex shading frequency, and I will tell you when it happens and when it won't happen. This is S.R. Chakravarti. He is a very famous professor at IIT Madras in thermoacoustics. Actually you can also see this kind of situation in combustors. The one pulse combustor that I have follows this, I think some of you have seen it, the one in the RM lab, and there actually the fuel injection is right behind the bluff body. So it is non-premix, but it gets premixed very fast, it is like that industrial premix combustor. So since the holes are very close, you actually have equivalence ratio fluctuations, and the equivalence ratio fluctuations actually go like the acoustic field. So then the thing shifts to the acoustic field, whereas in these experiments actually I think the fuel is injected way up. So by the time the fuel air mixture reaches the flame, the equivalence ratio fluctuations are kind of smeared out. So it actually so the vortex shading is the strong periodic thing, and then sound is going towards that. And the precise way of how, I mean the natural frequency is changing, it must be because while the lock on happened the impedance has changed or something, I do not know the details, but you see this scenario and this scenario in different combustors. So with I just very briefly mentioned to you this paper, you can have it, I can give you the PDF. I just mentioned this very briefly to show that still there is a lot to understand. This is a very recent finding, 2007 actually, and it is a very exciting subject and there is a lot to be learned, and there are 214 references to be read in that which are given in that review paper. So if are there any questions? So if there are no questions, I will mention briefly about passive control of these vibrations. Okay. So vortex coherent and the related periodic heat release can be minimized by manipulating the chamber acoustics to reduce the shear layer forcing field. So if the shear layer is responding to acoustics and is rolling up more coherently, so if we can somehow dampen the acoustic field with some passive devices, then this periodic roll up and all that, its coherence and strength would come down, so then the threat of instability will be lower. So what people do is to either put orifices upstream in the duct or put dampers or Helmholtz resonators or quarter wave tubes when you have a at a location close to a pressure maxima, you can put a Helmholtz resonator or something, so that it absorbs a lot of the energy. So that is one possibility, and the other possibility which is difficult is, okay, you can try to make sure that the hydrodynamics and vortex have different frequencies. So the vortex shedding happens at one frequency which is far away from the hydrodynamic field. Now if you are at this boundary and you can keep the hydrodynamic frequency lower than acoustics, but once you are here, whatever you do, okay, you may shift one this way, one other way, but then if not, the first mode, second mode or the third mode will get excited. So if they are quite far, then I think that is the simplest thing to do. And the amplitudes can be adjusted by adjusting the inlet length and the outlet length. So if you change the if you change the combustor length, you can change the frequency of the acoustic field. So that is another way to manipulate the frequency of the acoustic field. If you change the inlet diameter or the step diameter, then you can actually change the frequency of the vortex shedding. But the problem is when you have made all the combustors and then the designer would not let you change any of this, then the only possibility is to put this damping devices. Now another possibility is to, of course we can damp out, we can also change the driving if we can somehow get P prime and Q prime out of phase. So I was remembering an episode from Star Trek where, I don't know, the Enterprise is stuck somewhere and can't get out of the gravity, and then the solution was change the gravitational constant. So in Star Trek you can say whatever you want, but in reality it is very difficult. So here so you can I think it is not as bad as it seems. You can actually change the phase between the heat release and the pressure. So you can change the mixing time by different injection strategies, or you can change the location of the flame by changing the velocity with which the things are gases are convected, or you can change the fuel injection pattern, and if it is if you are having actually spray, then you can actually change the spray nozzle and change the spray the size distribution of the droplets that are coming out. So there is some things that is under your control. Of course many times you calculate something and you think you should go this way, and when you go the other way things may work. So if you have some idea, I would try the opposite thing as well, just to see which works. That is really, to be honest, and then give explanation afterwards to get faster solution. If you talk about annular combustor with several burners, as I mentioned, I think somebody asked this question, and then you can have each of them having a different delay, so that you do not have a coherent bang, but you have distributed heat release, so that the heat release is smeared out, the heat release oscillation is smeared out. So any questions on this? There are a lot of ways of passive control, but I mean these are some of the strategies. Okay, I will let you write down these things. In the meantime, I will drink some water. So let us summarize whatever. Yeah, you have a question.
In that picture, dominant frequency was Reynolds number what you have drawn.
Yeah.
There is no intermediate state, no. In actual situation,
you mean whether it goes from here to here?
Yeah, in this only lock-on frequencies are there.
Yeah.
But in actual case, there will be a lot of intermediate steps.
Well, let us do a demo.
Yeah. There is no intermediate, it is just here or there. I think I should not risk my
flute playing skills. It's 20 years since I played. I take it out every year for the acoustic class and then go back and deposit it safely. But let's try again. Some other note. So there was, you just get the note or it's harmonic, I mean, or whatever is the other duct mode. There is no in between. In between you can get if you do then everything is there. The non-lock-on situation, then you get a broadband thing. So there the spectra will be like it will be still modulated by the natural modes, but if you look at the two spectra, when you have a tone you have very sharp frequencies, but if it is not a tone the spectra would look something like this. So this is power versus frequency, this is how it looks like. Whereas if you make that sound, this is what you get, and the nice sound from the flute would be something like this, and typically there are even 10 harmonics and so on, but in between thing.
So that means that if you once lock on any,
so you have to change the mode. So then if you have locked down here and you want to get in between thing, you have to change the length by moving your fingers.
Yeah, but in a combustor case, that means once you lock on, any Reynolds number increase will lead to another frequency lock on.
So you are locked down here, or see in this situation the frequency will continuously change because you are locking to the vortex shedding mode. So here if you increase the frequency, it will keep on increasing the frequency, then it will jump to another mode and then keep, or the other way. But whereas in this kind of situation where let us say your injection holes are near the step or something, and then you are locked down here and you keep increasing the flow rate or the Reynolds number, and you won't change the frequency till some time, and then it will abruptly jump to a higher mode.
So we cannot have a safe situation in between at all.
So once it locks till it gets out, and it's a big range, and then it will lock to the next one. Here also, I mean, here the frequency is changing, but it's not safe. It is large amplitude under this frequency actually. Okay.
What is the order of magnitude of these dominant frequencies in combustion?
Same as that of flute. When the combustor is this long, you will get this frequency. This, okay, the speed of sound will be different. So let's look at a combustor which is 1 meter long. So L equal to 1 meter, and average speed of sound, let us say, is like 600 meter per second because it is a higher value. Of course in reality you have to solve that problem which you solved earlier. You have to know the temperature, you have to solve the eigenvalue of that Bessel, some equation was there, or numerically find it. So C by 4L, let us say, it will be like, and if you have a dumb combustor and the inlet is small, it will be like a closed end, or close to a closed end. 600 divided by 4 into 1, this will be how much? 150 hertz. Did I do it correctly? Yeah. So it's of the order of 100 hertz, 200 hertz, or even 50, 60 hertz.
We can probably design the combustor such that it can like withstand some frequencies. Like let's say 150 hertz frequency, if it can withstand, it can
See, frequency is not what you are withstanding, it is the amplitude whether you are withstanding. So for example here I am playing, I do not know, some frequency, it is like 400 something hertz or something perhaps, and nothing happened to it, and some other flute I might play 250 hertz or 270 hertz, nothing happened. So if the amplitude is small, any frequency is okay, but if the amplitude is large, there is a problem. And the other issue is there anything, your combustor may not break up, but something else in the aircraft or something will have the natural frequency at this frequency, then there is a problem. But if that does not happen, if that is ensured that those frequencies are different, then it is a question of how large the amplitude is. or certain frequency there is a tendency to be driven, and then you can change the combustor frequency. I do not know if that is what you meant. If the driving can occur in a certain frequency range, you make sure that the combustor frequency is out of the range. Is that what you are saying? Can you restate your question in some other way so that I understand?
So structurally designed to withstand
some particular frequency more.
Yeah.
Even structural mode will vibrate in that sort too.
Yeah, so yes, I mean if there is no problem with structures, you can have a frequency. I mean this is a good example. No, nothing. If the fluids break up with this frequency amplitude, then there is a problem. So it does not break up. So but the problem is if you I mean we want lightweight and do not use material and all that, if you make it like big and fat, then it will structurally withstand, but then you do not want to do that also. That is the problem. So I think an engineer will not accept that solution to make your engine robust by making it massive or something. I think he would ask the combustion engineer to reduce the amplitude somehow. Frequency, yes, you will ask to change the frequency if something else. So let us say you have a low amplitude oscillation. Some missiles I have heard you have well, this is recorded so I cannot give the names, but so you have a missile, it is working fine, or a rocket, it is working fine under static test, there is no problem, and it is fired also fine, no problem, it goes into service. But if the missile is there in service, every now and then they will take out a missile and fire just to check if it works or not. It is like shooting practice, like if you are a soldier you have to shoot so many rounds per week or some such guidelines. Similarly, just to make sure that the weapon is working, it will be tested, right? And then you test it and then suddenly it blows up, and then you panic and want to test another one, again it blows up, and then you go back to the test stand and make a test without flying, and then everything is fine, the oscillations are almost nothing. Then it turns out that the oscillations are very small, but there was some component in the navigation system which is also which vibrates and spoils, and electronics is very sensitive to sound, right, sound and vibration. So under such then the easiest way is to rather than kill the oscillation, already they are very low, and anything you change may actually make it bigger, so change the natural frequency of the navigation system so that it does not vibrate to this. So under that circumstances, or you change the combustor length slightly, but in a existing combustor it works, nobody will let you change anything actually. The designers are saying do magic but do not change anything, or add some magic powder into it and get it to stop or something. That is pretty much what the rocket instability people say. But so in this case it is easier to change something with the way the electronics is mounted, and you can change the frequency of that. Is that what you are asking? Okay. So we are not really changing, like changing the combustor frequency is not really getting rid of the oscillations, but there is a roundabout way when your oscillations are low but something else is locking in. Anything else? Okay. So in summary, in the last 2 or 3 classes we looked at instability associated with formation of large scale vortices in the mixing layer, which coupled with the acoustic pressures to excite strong oscillations, and we looked at cold flow results, and we saw that we are having Kelvin-Helmholtz instability, and we looked at some brief theory, and we saw that the linear stability theory predicted a Strouhal number of 0.017 at the initial layer, but then there is vortex merging and so on, and then at the there is a big vortex and which is having a lower frequency, and it has like a Strouhal number based on jet diameter and the velocity at the exit, and that is like 0.25 to 0.5, that is the preferred mode. And if you excite at that frequency, then there is a good chance that the vortex will become very coherent, and your oscillations will be excited at very large amplitude, and then the combustion gets periodic along with this vortex shading. And although in cold flow you do not see very large amplitude unless there is this kind of edged on kind of business or a lock-in kind of business, but when there is reaction happening, that is a very strong monopole source, so periodic heat release happens, there is feedback, and the mixing layer rolls up into vortices where combustion occurs. So if you have a dumb combustor and you just blow air, you will not hear anything. That is why in flute they have that labium, and that the vortex rolls up from there and hits on the edge and makes the sound. And the energy release, so once the mixing layer rolls up into vortices and combustion occurs, and you now then start having the energy release being periodic in nature, and this will reach a maximum when the vortex is breaking down into fine small scale turbulence and the combustion now suddenly happens. And so there are different mechanisms which lead to this transition, and I told you it is a very advanced topic. Vortex interaction is there, interaction of vortices with walls is there, and so Kelvin-Helmholtz instability may come, but there is also this flapping mode instability. We also looked at flame-flame interaction, and that causes the flame wrinkling and so on. So in any case, a lot of different mechanisms all lead to fluctuating heat release, which if it is in phase with the heat release rate will lead to which if it is in phase with the acoustic pressure will lead to large amplitude, so there is acoustic driving. Now this goes by the Rayleigh criteria. So one way to control the oscillation passively will be to change the phase, that means you change the time delay somehow, or you change the location of the heat release zone. That way you are changing the impedance. You have a certain phase between heat release and velocity, but there is also a phase between velocity and pressure, and what matters for driving or damping is the phase between heat release and pressure. I hope you understand this. In many of these processes you have Q prime and U prime have a phase, but what you want is to look at the phase between Q prime and P prime, and so you can change that by changing the phase between P prime and U prime. That can be done by moving the flame to a different location where the impedance is different, P prime over U prime is different, and that is another strategy to do passive control, which is why the flame location is a very important bifurcation parameter. So you can change the geometry, you can put dampers, or you can have a host of mechanisms to actually passively control, change the length, change the diameter, or keep these frequencies away. So I will stop here with this, and in next class we will take a look at the very briefly on what is the active control of combustion instability on similar combustors, and then we will after that we will speak a little bit about solid rocket motors and instability there, and if time permits liquid rocket motors.